Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guest today is Dominik Ulmer, Chief Quantum Solutions Officer at ParTec. Dominik describes ParTec's transition from a traditional HPC software company to one integrating quantum computing into their offering. He explains their approach to hybrid classical quantum systems, highlights the importance of minimizing new infrastructure requirements, and their support for hybrid on-premises and cloud integration. He also outlines ParTec's physical integration lab, future plans for a Quantum Workbench, and much more. We hope you enjoyed this episode. Hello, Dominik. Thank you for joining me today.
Hi, Yuval. Great to be here.
So who are you and what do you do?
Well, I work for ParTec, responsible there for their quantum AI products. My background is in HPC. Actually, originally I'm a geologist, but that's former life almost, I would say. And I joined ParTec about 3 years ago to build up a new direction of the company, because as an HPC company, we're always interested in anything that pushes out the boundaries of what's computational possible. And quantum obviously has a lot of potential there for us.
And what does ParTec do?
So we are we have been mainly a software company until 3 years ago. So developing software that allows what we call modular computing, so heterogeneous HPC systems, managing those systems, optimizing performance on these systems, enabling communication between those systems. And we decided about 3 years ago to look also at other technologies on non-classical compute. And obviously quantum computers embedded in an HPC system match our let's say, ideology, or let's say a strategy to build heterogeneous systems.
If you think about hybrid classical quantum applications, it sounds like your software can connect the classical side to the quantum side. What is common between classical and quantum computers as far as you are concerned? And what is different between classical and quantum processors?
A lot of differences. I think that's what you've noticed first, So let me explain our approach, how we do the integration, so that you see, what our, let's say, main target is in this integration. And we are coming from a customer perspective. So we think that quantum computers will actually be an important element in academic or research-oriented HPC centers. And they have, of course, established a way how to operate those systems and how to use these systems over the last decades, and they don't want to change these things. So our approach is to virtualize the quantum computer as a special node in the HPC cluster. And that way it can be managed by the sysadmin, in a way that they are used to, as much as this is possible from a physical point of view. And it also allows, let's say, the way the user access is managed and the usage is managed to be the same. So we can project, let's say, priorities, compute time allocations, or even also security and so on this system. So that's how we approach this. Now, for the user, then you have to. It's a little bit like programming a GPU system, if you want. You have to identify those elements in the code that you want to run on the quantum computer. You will have to use a completely different programming style for that than on the classical side, and you will offload these systems. Now, and this work. And what we have to understand, and that's really future, or let's say the research that's going to happen over the next years, is to understand how that offloading works, how close these loops between the classical and quantum have to be, what type of algorithms gives you the initial advantage, and so on and so forth. So we're currently at the point where we're building the infrastructure, and we also want to build not only the software for the integration, but we also want to establish ourselves as an integrator on the hardware side. So really acting very similar to what has happened in classical compute, where you initially had monolithic systems where everything came from the same company. And then now we have a supply chain of technology providers which allow you to integrate these systems. And we see that, let's say, the heterogeneity on the quantum compute side, how these systems behave, is of course much broader than in the classical side. Standard CPU, yes, there are differences between an ARM or an AMD or an Intel processor, but the way it basically behaves, is very similar. And that's not the case between different modalities, let's say, of quantum computing. That's very, very different.
Let me dive deeper into that. I understand that the programming model is different. I understand that it's different. CPU and GPU and QPU code is different. I understand, or I think I understand, that some things like security and reserving the resources are probably, or maybe billing and priorities are probably common across all types of computers. But other than the code itself, what is different from your viewpoint between classical and quantum?
Okay, so I ran a computer center myself, for 9 years. So I can tell you it starts already at the infrastructure side. So let's say if you have a cryogenic quantum computer, that means a lot that you have to prepare as a customer. You have probably completely different requirements how the data center infrastructure has to look like. Actually, what we try to do is to identify those technologies or those approaches that allows you to fit into as much as possible into this. So that you don't need, let's say, an anti-vibration, let's say, concrete block under the system, that you don't need maybe special certifications like liquid nitrogen handling, things like that. So that's what we try to avoid as much as possible. That's where it starts. It's also not a system where you as a customer can manipulate a lot yourself on the hardware side, or you shouldn't. So that's also very comparable to the early HPC areas where when you bought a Cray machine, you bought basically 2 engineers with your machine, and they were there sitting on site. And that's probably very similar for quantum computers nowadays. And then if you jump into the user side, what we currently see is that the user first has to learn to think the way how you program a quantum computer. You have to see that a user community of an HPC center that would try such a system has very different expectations. There are quantum information scientists who know exactly what they have there, and they explore the capabilities of the system. And then there are maybe domain scientists who think they can achieve, a scientific result using that system. And that's probably where we currently cannot offer them really a solution. But the idea is to make these systems available and then enter the path over the next 4 to 5 years, so that, let's say, a quantum chemist can run a common quantum chemistry simulation using that system. So I think there's a lot of difference on the technical side. The way it's programmed, it starts already with the languages that people use. So classical HPC codes are, in the worst case, they're still using Fortran. Some of them, most of them use C++. Now, in quantum computing, Python is the base that people use. You have in the tool chain, I think, very well established, components on the classical side. How the compilation and all that tool chain is well established and very similar over the various systems. These are things that standards that still have to be found on the quantum side. There are some quasi-standards that we got from IBM, but things will change over the next years to come.
I understand the differences on the hardware side, but I'm wondering if on the system management side, so for submitting a job, is it any different? Resource allocation, is it any different between classical and quantum? Obviously, the cryogenics and the coding language and the tool chain is completely different. Yes.
So, of course, if you virtualize your quantum computer in your HPC cluster, it's a very expensive node compared to the others. So you don't want, and typically in an HPC cluster, a user books a node completely for themselves, for their job that is currently going on. Probably would like to avoid this for this very expensive node. So this must be a shared resource. So where you do kind of allow simultaneous access by various jobs in order to maximize utilization and don't have long wait times. You may also, and this is something we are exploring, adding to our integration software also an emulation software. You don't want every user to go immediately on the real hardware, because when they're in an early stage, that's too expensive again to let them on. You may have in a cryogenic system also extended downtimes, that you don't experience on a classical computer. And a classical computer may fail a node and then you replace something and you boot it again and they're done. Here you have to warm up, change things, cool down, may be gone for several days. So an emulator where you have the real noise model of the observed physical system is a very useful extension, basically, that you have to add. So, the resource management and also the way resources are presented to a user is, from that perspective, very different.
We spoke a lot about cryogenics, which of course is a concern when doing superconducting computers, but there are other technologies like neutral atoms that do not require cryogenics and operate at room temperature. Does your software platform support all types of quantum computers or just specific modalities?
So we started developing the integration software together with Quantum Machines as our partner. And they basically can drive all types of modalities. However, we started in the design, how we do, let's say, the multi-user access and things like that, assuming characteristics of a typical superconducting or silicon spin qubit solution. But fundamentally, we can, from that perspective, drive any modality in the way the software was developed. And we have a project, or let's say it's more than a project now. It's soon going to be inaugurated and go into operation, the Israeli Quantum Compute Center, where we work together with Quantum Machines and many other partners to offer access to 3 different modalities initially. That's going to be a superconducting, a neutral atom system, and I think a photonics annealer. And this will be integrated with classical resources that are partially on-premise, but mostly in the cloud. And we have developed a platform as a service solution, which allows you to log into this virtual cluster on the cloud and then access those 3 different modalities, and we can add additional ones over time.
You brought up an interesting point that I wanted to ask about. Certain users are buying quantum computers on premises. Some have classical supercomputer on premises, but they still want to access sometimes cloud resources, either for the quantum or classical side. Does your software platform support this hybrid situation where some jobs could be executed locally and some jobs could be executed on the cloud?
You could do that, yes, absolutely. Actually, the way the integration software works currently, it integrates into what we call a Slurm cluster. That's a way how you can manage a parallel HPC system. But the way the system, let's say the software was designed, we can add, let's say, other workload management types to this, not only other, let's say, HPC workload managers, but also we can integrate it in a Kubernetes cluster or some other, let's say, way of running a multi-resource, environment with cloud jobs.
Does ParTec also do the physical integration? So if I wanted to set up a new quantum center, would you help me both with the physical installation, cabling, preparing the nitrogen if I need, and as well as the software one?
So actually, we started exactly this. So as I described, we started from the software side for the integration, and now are in the process of setting up a lab. We could say an assembly site in Munich, where ParTec is located, where we will use this component-based approach for building systems, using let's say technologies that we get from suppliers and integrating them the physical system itself. And we will also develop calibration software for this and so on. So we're currently in the building process, and we hope to be ready by the end of this year or the next year. And the idea is to do both things. And what we see in the market is, on the one hand, a lot of the procurements basically prescribe exactly what you have to build. And then it's basically a custom engineering project that you do for that customer. But what we want to do then in what we call ParTec Quantum Factory is to derive from that more a set of standardized components that we put together and that we can vary in a kind of Lego style and then have a real product. And that product is going to be available as a superconducting solution initially, because that will focus on superconducting initially because of maturity of the technology at this point, and also availability of that supply chain. And we think we will have that product available early next year as well, together with the factory.
In your experience and estimate, how long does it take? So let's assume I decided on what computers I want to buy. I have space. The computers were delivered. They're waiting in boxes. How long before my HPC center could be up and running in some fashion?
So everything has been delivered. You take out already quite a bit, because some lead times of components can be quite extended. We did 2 of these integration projects already, and let's use the example what we did at the Munich Research Center in Germany, where we had an existing cryostat that was kind of already operational that we could use. So we have to take this into account. But from, let's say, delivery of the QPU to integration, not only of the hardware, but also integrating in the local supercomputers, it took us about 3 months at that point. And that was our very first system. So there's, of course, still a lot of work to do to make it even more useful. But let's say that's when users could get on the system.
You mentioned Slurm. Is that, in your opinion, the dominant standard for resource allocation and so on? Or do you support other type of frameworks?
Well, in HPC, in academic HPC, I would say Slurm is the most widespread solution. The way, as I described it before, of our integration software called QBridge works, we can easily extend this to other workload managers, or also even to cloud-style workload orchestration platforms. That's pretty easy, I would say.
As you think about your product line, say 2 years into the future, what's the biggest thing that you think people might want in 2 years that they don't have today?
Oh, very good question. We will find out. So, as I said, we we consider the software that we now are finalizing and delivering. QBridge is already released. The emulator and what we call also the workbench, because we think one of the things that we know from AI, so again, we are taking a lot of analogies from classical compute. What we've seen there is that people are very eager to store, let's say, the experiments, not only the results, but also the way they run the experiments so that they can reproduce those things later. So we want to build something similar for quantum. So we call this the Quantum Workbench. And also then the tool chain that we have to provide for software development. These are all MVPs, so minimal viable products that we make now available. We certainly want to have, let's say, a very kind of capability on the integration side that we allow very short and frequent exchanges between the quantum computer and the classic computer, maybe with less latency than we have now in our current solution. Because once you have you want to run real experiments, not only proof of concept, but real experiments and get quantum advantage. The applications that my team has seen so far probably want to have this very, very frequent and low latency exchange between the two systems. So that's something we will work on. And on the emulator side, I think what they will try to do is, or what they want to do is to have maybe different types of simulation codes behind it so that you have a kind of choice. And what we hopefully will see is that people will, exactly what you described before, want to try to use different modalities on the physical side and really run and characterize them and compare them. That's, I think, that would be the direction that many people will try to take, and which we want to support. Now, what the exact requirements are going to be, we will find out, I think, while we're working together with them, because what is generally our approach is that we have a very close collaboration. We don't want just to ship something and say, okay, here it is, and we are going to exchange the failing parts, but really work with them together on improving the usefulness of that system over the years. And that is kind of what we call a center of excellence approach that we want to do together with our customers.
Very good, Dominik. Thank you so much for joining me today.
Welcome. It was a pleasure talking with you.